Okay, there's one last little bit we'll talk about before we move on to the next section. Yes, you are a very good boy. Sorry, the dog just came up and put his face right in my hand. Anybody who's interested, hey Pippin, can you say hello? Yes, you're a good boy. Okay, he's kind of always right there when I'm doing this, so every once in a while, he's probably going to make a cameo. Okay, where was I? Yes, okay, so we're going to do kind of a slight sidetrack, but it does apply to one Mastering Physics question, and it's really super interesting and cool, and it applies to the course as a whole, especially when we circle back around to electromagnetic waves. So when we have a traveling wave, the position of the wave changes both in time and space. So the height of the wave, it depends on where it is and when it is. Good question to ask is, are those changes related? Is the way it changes in time related at all to the way it changes in space? That's a good question. So the way it changes in time is something we've already figured out. We found the transverse acceleration by doing the second derivative of position with respect to time. That was our transverse acceleration. We've already got that one sorted out. So there's our form for that one. And I picked here a rightward moving wave, but this applies just as well to a leftward moving wave. So we can also follow the method we used here to find how it changes with regards to space. So we did the second derivative with respect to time to get this for a result. Let's do the second derivative with respect to x and see what we got there. And then we'll have a look at those two things together and see what that looks like. So the second derivative with respect to x means we'll do the derivative of the derivative. So let's get this guy sorted out. So if we're solving this one, first thing we do is we take our a outside. The derivative of sine is cosine. And then we have to multiply, we have to finish our chain rule by doing the derivative of the argument. What's this equal to? Well, the derivative of kx is k, derivative of omega t. Remember, we're doing a partial derivative with respect to x, which means we take t as a constant. So derivative of constant is 0, so that part's going to be 0, and the derivative of phi naught is going to be 0. So we've got a times cosine kx minus omega t plus phi naught times k. So a times k times cosine kx minus omega t plus phi naught. Okay, that's this part. Let's plug this in right here, do the derivative again, and we'll get our final expression. So for this guy, we take our ak out front. We're going to do the derivative with respect to x of cosine kx minus omega t plus phi naught. Derivative of cosine is minus sine. And then we apply our chain rule, so we have to do the derivative of the argument. So the derivative of kx minus omega t plus phi naught is just k. So that gives us minus a times k squared times sine kx minus omega t plus phi naught. So we can fill that in up here if we wish. So our initial question is, are these two changes related? So we see we've got a sine term here, a sine term here. Let's solve this equation for sine. Let's solve this one for sine, and let's set them equal because the two sine terms have to be equal. So if I call this guy equation 1, so this is going to be equation 1, and this one will be equation 2. I'm going to solve both of those equations for sine. So I'm just trying to stay a bit methodical here. So I'll rewrite my equation 1 first. Sometimes it can be a little bit easy to get lost in all the steps of this algebra. So equation 1 says the second derivative of d, I'm going to drop the of x and t because there's just so many symbols to be writing down, is equal to minus a omega squared sine kx minus omega t plus phi naught. So I just rewrote equation 1 there. Now I want to rearrange for my sine term. So sine kx minus omega t plus phi naught equals, I'll have to take this to the other side, minus 1 over a omega squared second derivative of d with respect to t. Okay, so there's one expression for sine. Now let's do the same deal with equation 2. Equation 2 says that the second derivative of the height with respect to horizontal position x is equal to minus a times k squared times sine kx minus omega t plus phi naught. I can solve this guy for the sine term by dividing my minus a k squared to the other side. Okay, so this is sine, this is sine. That means these two things have to be equal because sine and sine are the same thing. So this tells us that minus 1 over a times k squared, second derivative of d with respect to x, is equal to minus 1 over a times omega squared, second derivative of d with respect to t. So what do we see here? We've got minus on either side, we've got amplitude on either side. Let's bring the k up to that side. So the second derivative with respect to position is k squared over omega squared times the second derivative of position with respect to time. Okay, we can do something with this guy right here. Hopefully you remember that our wave speed v is omega over k. So then k squared over omega squared would be 1 over the wave speed squared. So that can come in here to give us second derivative of d, which is a function of position and time, with respect to position, equals 1 over v squared, where v is the wave speed, times the second derivative with respect to time of the position, which is a function of horizontal position and time. This guy is pretty important. Turns out this guy is really important. So this is the general form for any traveling wave. Okay, I worked it out using a sinusoidal wave. Turns out it's true for all the waves, for all the traveling waves. And this is something you would study more of, especially if you went on in a math class. So there's loads of math courses about this stuff. A couple of neat things here that will take some time to point out. There are two kind of extreme situations you could have. If you have a place where the amplitude is pretty small compared to the wavelength, and that's going to be the waves that we study. So if the amplitude is a lot smaller than the wavelength, that would be something like a wave on a guitar string. That gives you a linear wave. A lot of that analysis is fairly straightforward and the math is not too complicated. It gets to be kind of fun if the amplitude is a lot bigger than the wavelength, so you get a huge vibration vertically on a small scale horizontally. Those waves are nonlinear. Super interesting to study, but definitely beyond the scope of this course. So we're going to stay in this regime where A is less than the wavelength, but it is good to know that you don't have to stay there. You just have to be careful with your treatment if you get your wavelength too big. Okay, last, and here's where I think the most interesting thing is, James Clerk Maxwell, he took this expression and he applied it to the electromagnetic wave, a light wave, and that's how he proved that light was a wave, and how he found that the speed of that wave was constant for all the electromagnetic waves and it was equal to c. So that's kind of a super interesting thing about this, and we're totally going to circle back around to that, but not till the end of the course. Anyway, still cool to mention here that Maxwell used an equation to show that light was a wave. I think that's really neat. Anybody who says math is not cool, I would say that they're totally wrong, because math is pretty cool if you can do that sort of thing. Okay, so that clues us up for now, and then we'll move on to another section.